There it is. Okay, so today I'm actually I'm excited to present to you Matilde Mingozzi, a ESA Aura staff member at the Space Telescope Science Institute, who will be talking about UV spectroscopy and the very first galaxies. And I think I recognize that background picture, but yeah, I'm not going to spend much more time talking. I'm going to start listening, and Matilde, please take it away.
Thank you very much. I'm very happy to be here today and to have the opportunity to talk a bit with you about the role of UV spectroscopy to interpret the properties of the first galaxies, and in general to brainstorm together about the future with HWO. And thank you for the organizers for this very interesting series of talk. I will talk about works that I've been doing in collaboration with many people. I highlighted here some of the names, and in general I want to highlight the classy team I've been collaborating since like end of 2020. So I will start my talk from the few among the questions highlighted in the ASTRO 2020 decadal surveys, open questions for modern astrophysics, because among the other things, we still don't know which properties characterize the first galaxies and how did the systems reunionize the universe, and what is driving the growth and the evolution of galaxies over cosmic time. These are open questions. They are mostly related to the high redshift universe, and now with JWST we are learning more and more. But definitely this is the future. So this is how we need to understand how to use the current and future instruments to find an answer to these very big and broad questions. So here I just wanted to highlight some among the processes that characterize the evolution of a galaxy, of galaxies. For example, here I included mergers, so major and minor mergers, gas inflows, because the inflow metal poor gas can provide new fuel to form new stars in galaxies, and also diluting the metal content of each system. Then definitely we have star formation with stellar winds and supernova explosions, so with the stellar evolution that is providing metal enrichment to the gas in galaxies, and also through stellar outflows, through galactic outflows due to stellar feedback, some of the metals produced and present in the gas in galaxies are ejected out from the galaxy, going to enrich the circumgalactic gas, circumgalactic medium, intergalactic medium, while some of these metals instead stay inside the galaxy. Of course, we have an important character is also dust, AGN activity, AGN that can act as a flashlight, ionizing all its surroundings, and providing negative feedback through jets and gas outflows, so basically heating or removing gas from galaxies. So all these processes are part of the so-called baryon cycle, and this is a beautiful cartoon from Tomlinson, Peebles and work that clearly shows all these processes together. And one of the way that we have to find an answer to the questions I highlighted before that are also here on the top of this slide are to study, so one of the possible approaches is to study the conditions of the gas within a galaxy. And among the properties of the gas in galaxies, one of the most important one of the most informative one, is definitely the metal content, the gas metallicity in particular. And so here on the right, I'm just showing you the most recent version of the so-called mass metallicity relation, because the gas phase metallicity is found to correlate with properties of the galaxies, including the stellar mass. In the nearby universe, I don't know if you can see my cursor, I hope so. In the nearby universe with SDSS, we found that the metal content is increasing, going at higher and higher stellar masses. In this current version of the mass metallicity relation, you can see a lot of galaxies between redshift 3 and 10 using JWST recent studies, but not only. And you can clearly see that there is a lot of scatter that still needs to be understood, definitely. But I think that like the picture here on the right basically is reflecting a bit what we see on the left. So there are definitely pristine inflows that are diluting the metal content of the gas, and then star formation and ISM evolution that are increasing the stellar mass and the metal content of galaxies, and rich outflows that are pushing out gas from enriched gas from galaxies. So definitely the study of gas properties can give us information, can allow us to constrain all the processes I mentioned before because of these reasons. So why this is one of the reasons. So to do this, to study the galaxy properties, one of the most powerful tools has always been optical spectroscopy. Optical spectroscopy has been used in the past 30 or more years to study the ISM. Here I'm just showing a spectrum that goes from the oxygen 2 to the sulfur 3. I highlighted some of the lines saying which are temperature sensitive, which are density sensitive, others are sensitive to the ionization source. And then we have also the Balmer series that is sensitive to the gas, the attenuation of the dust. So definitely a lot of information can be gained from all the features that are enclosed in optical spectra. And apart from these, we can also learn information about the gas kinematics and the presence or absence of outflows by studying the line profile of the emission lines. And to do this, there are so many instruments. Here I just highlighted some of them, and there will be more in the future. So there are a lot of instruments that we can use to do this kind of science. And this is optical spectroscopy. Moving to UV spectroscopy. So this is a UV spectrum going from the Lyman alpha to the carbon 3. Here I highlighted just the main emission lines that are visible here, definitely less with respect to the optical for the emission lines. And to study UV spectra in the nearby universe, one of the instruments that can be used is COS. COS allows, if you put together these three gratings, for example, to do very high signal to noise, high spectral resolution studies of the entire UV range. But actually, apart from the few emission lines here that I highlighted, there are many more features that are hidden in the spectrum over here. And this is because the UV spectra, first of all, they allow us to constrain the properties of, like, they allow us to constrain the young stellar populations that are ionizing the gas, because the UV is extremely sensitive to that. So studying the continuum component as well as all the wind features in the spectrum, we can constrain the young ionizing stellar populations. Then there are all the nebular emission lines that we can use to study the ISM properties more similar to the optical. There are multiple absorption lines that can be used to study the presence of outflows, but also the content, the atomic the metal content of the atomic gas. There is the Lyman alpha that can there can be many studies on the Lyman alpha. So the UV spectrum is actually full in features, rich in features, comparable to the optical. And also another superpower of the UV is that the UV diagnostics can characterize the stellar and the nebular evolution across the redshift, because we have UV, res frame UV spectra in the local universe with HST. If we move at cosmic noon, we can have UV, res frame UV spectra using ground-based observatories. And if we move in the epoch of reionization, where many of the questions I highlighted before are related to, are coming from, then with the res frame UV is shifted to the observed infrared. And so JWST and the future infrared observatories are definitely tracing the res frame UV for the most high redshift systems. So linking this to the next slide, I just want to go back and look at this is a very famous cartoon of the cosmic timeline. showing the main epochs of the history of our universe, including the Dark Age, where the first objects were born, the epoch of reionization, where some of these galaxies, where photons from these galaxies escaped, reionizing their surroundings, and then you can see the galaxies evolving till the shape and form in which we see them today. And as I was saying, JWST now, so infrared observatory, like JWST now is giving many more information about the epoch of reionization for the first time, showing objects up to redshift 13 spectroscopically confirmed. Future observatories, for example, the ELT, will give us even more detail, like even further detailed studies. And from a statistical point of view, we can count on future missions, like current and future missions such as Euclid and Roman, that are supposed to reveal thousands of galaxies at redshift higher than 8. So in some sense, complementing more detailed studies that can be done with the JWST and the ELTs, for example. Since before I was mentioning the importance of the UV, what JWST has been doing at the moment, these are just two examples, two very important, like two galaxies that JWST, two spectra that JWST revealed, are this galaxy at redshift 12.48, which at the moment represents the farthest galaxy with emission lines revealed, to my knowledge, and the GNZ11 at redshift 10.6, which is a very UV bright source, very peculiar, and is also thought to host an AGN. And the two important things that I want to highlight here in these slides is really the rest frame UV that is basically dominating the emission lines in these two spectrum, because the majority of the optical features that, as I was saying before, have mainly been used to study the optical properties in the history of astronomy, are out from the observed wavelength range of near spec. So in order to answer to the questions of the ASTRO 2020 decadal, we need to understand better objects at this very high redshift. To do this, we need the UV. We need to use also the UV information from their spectra. What can we do to do this? First of all, so we can use the nearby universe to do this. We need to understand which kind of properties, more or less, these galaxies are tracing. Going back to the gas phase metallicity, the mass metallicity relation I was showing you before, this is the position that the two galaxies highlighted here are tracing. And in general, looking at galaxy between redshift 3 and 10, we are looking at very metal poor and low mass objects. So these are the kind of objects that we need to highlight. These are the kind of properties that we need to target. And we can use the present-day universe finding analogues to these high redshift systems using their S-frame UV and also optical spectra to understand their properties and their processes, and then use these to interpret the high redshift results. To do this, there have been many studies in the past few years. I want to highlight here the work that has been done with the CLASSI survey. CLASSI stands for Cost Legacy Archive Spectroscopic Survey, a treasury of star-forming galaxies, and CLASSI represents at the moment the largest survey of star-forming galaxies with full rest frame far UV coverage and high signal to noise. It uses COS, of course, and and the sample spans a broad range of stellar and gas properties. In particular, here to be very short, I just got a picture from the CLASSI presentation paper showing the star formation rate as a function of the stellar mass, where you can see the CLASSI galaxies as purple dots. And you can see that with respect to the nearby universe that is shown from the turquoise and the blue line, the classic galaxies have higher star formation rates, which is more consistent with the high redshift universe. And apart from this, they also have they span a broad range of gas phase metallicity, ionization parameter, and so on, but keeping also galaxies that are highly representative of the high redshift universe. Of course, apart from the UV, using COS, we also have optical spectra that we can use to make detailed comparisons. I want to show you one of the spectrum from Classi. This is a very famous nearby blue compact dwarf. This is the spectrum. In purple, you see the spectrum obtained with COS, very high resolution, high signal to noise with compared to the previous version of the spectrum. This also allows us to understand the importance of the spectral resolution for a future instrument, because a very high spectral resolution allows to better determine the emission lines, also allowing to determine, for example, the carbon-3 is a doublet, so allowing to resolve the two lines in the doublet. And also revealing absorption lines in the spectrum that can be used to do studies of the atomic abundances of the gas, but also studies of the presence of outflows and so on, among the other things. And another important thing is that, for example, concerning the helium-2 line, the helium-2 is a line that has both a nebular and a stellar contribution. It can have a stellar contribution, and the stellar contribution is known to be much broader. So a very high spectral resolution allows to distinguish between the two components. So this is something very informative that we need to keep in mind, to bear in mind for the future observatories. Anyway, going back to my work on Classi, one of the things we wanted to understand is how these UV diagnostics could compare with the ISM optical diagnostics to interpret the high redshift universe. And to do this, we started to look into different ones. And I want just to show a couple of results before moving to a more general discussion. In particular, we could find that in the UV, there are density tracers, such as the carbon-3. The carbon-3 line ratio is one of the main UV density tracers in the available spectrum, in the covered UV spectrum. And when we compare UV densities obtained with these UV tracers with the densities obtained in the optical, for the same objects, we can get very different results, and up to 2x if we use for the optical the sulfur-2 doublet. And this is because when we measure gas properties, we need to take into account which ionization zone we are tracing with that specific, like how we are measuring a specific properties. In particular, the carbon-3 and the sulfur-2 are not tracing the same ionization zone. The carbon-3 is tracing much more ionized gas, like intermediate ionization zone of the gas with respect to the sulfur-2. This is probably leading to the discrepancy. So this is something that is important to take into account every time that we are comparing something that is measured in the local universe and something that is measured at high redshift, like how we are measuring that specific property. Then, of course, as I mentioned before, a very important thing is to understand the gas phase metallicity. To measure the gas phase metallicity in the UV, it's a bit tricky if you don't have a way to measure directly the temperature. But we found some indirect tracers, for example, the carbon-3, oxygen-3 line ratio, or the equivalent width of the carbon-3. The issue is that the UV lines are very sensitive also to other properties, such as the ionization parameter, which is shown here as a color code in these two plots. And in general, there are some caveats that we need to take into account. For example, for the equivalent width of the carbon-3, it is true that the equivalent width of the carbon-3 is increasing going at lower metallicities. So there is a clear anticorrelation that can be used to infer the gas phase metallicity. But then when we reach 7.5, more or less, there is a much more scatter because there is a turnover of the relation. But this part of the diagram, unfortunately, is not very well populated because we don't have too many measurements of very extremely metal poor objects. So we need to have more objects in this part of this diagnostic diagram, among the other things. Another important property to constrain is definitely the main ionization source of the gas. In the optical, there have been many ways, there have been many diagnostics proposed to separate between star formation, AGN activity, shocks, etc. Here I'm just showing you one example, one diagnostic diagram, the oxygen 3 H beta versus N2 H alpha. And I just want to highlight that here you see different colors because the emission lines in the opticals showed in many cases very broad profiles that needed, and so we needed to do detailed we need to use multiple components to fit the emission lines. That is why there are different colors over here. But in general, we are pretty sure that galaxies like Class C are star forming, and so we can explore how these star forming galaxies populate diagnostics that have been proposed in the UV to discriminate between ionization sources. And this is what I'm showing you here in this plot. This is the same plot repeated twice. It's the carbon 3 helium 2 versus oxygen 3 helium 2. We superimposed star formation models on the left and AGN and shock models on the right. This, among the UV diagnostics that we explored, is the best one in our opinion, to separate star-forming galaxies from other mechanisms, because even the two most extremely metal-poor galaxies are still located close to the star-forming galaxies and are not superimposed with the AGN and shock models, which is something that happens using different diagnostic diagrams. This is because extremely metal-poor galaxies, like a very metal-poor metallicity, can mimic the condition of an AGN of a shocks, and so it can be difficult, it can be tricky to separate between the different mechanisms. But also here we would need more metal-poor objects in order to discriminate even better, like if this diagnostic diagram in particular is doing the job or not of separating the different contributions. So to conclude this part of Classy, I just want to say that yes, we created this UV toolkit that we hope can be informative for high redshift studies and can be used to try to understand how to measure the gas density, the metallicity, which UV lines are visible at which ISM conditions, and so on. And in general, with the surveys like Classy, we could actually provide much more than this. Like I was just talking about the UV diagnostics, but actually there have been works from collaborators on ionized gas outflows, on the Lyman alpha profiles, on the study of ionized gas abundances, and there will be in the future also studies on the carbon abundance, atomic gas abundances, and so on. So there will be, like from a survey like Classy, there will be a lot of informative information, that a lot of informative things that can be useful both to understand the redshift universe, but also to understand what we still need for a future observatory. And this is when I want to introduce, I want to talk a bit of UVEX. UVEX, which is has been recently approved, is a MIDEX NASA mission. These are plots that I took from this work from Kulkarni 2021, so probably this should be a bit updated. But still, I think that UVEX could fly at the end of like probably around 2030 or something like that. And UVEX will be the nearby future of UV spectroscopy because it will provide an all sky imaging survey and also a spectrograph. So will be both an imager and will have also spectroscopy. Will be similar to Galaxy, but with much more sensitivity, and it will provide the counterpart in the UV for future current and future missions such as Euclid, Rubin, and Roman. And talking about spectroscopy, because I am talking a lot about spectroscopy. UVEX will have a slit. It will not be a very high resolution slit, but medium resolution, let's say, with a resolution like around around 1000 or so. So not too high resolution, but with respect to COS, it is supposed to have a much higher throughput and so much higher sensitivity in both in the far UV, but also in the near UV, where the throughput of COS is a bit off with respect to what UVEX will be. And one of the pillars among the science cases and science themes that UVEX will cover is dedicated to the low mass, low metallicity galaxy frontier, because low mass, low metallicity galaxies dominate the local universe, but not enough of them are observed. And this is because of different reasons. First, because they are faint, and also because they are spread across the sky. So UVEX since it will do an all sky imaging survey, is supposed to reveal many more metal poor low massive galaxies, and the UVEX discovery space in particular will be this region over here in this plot on the right. And one of the reasons why the UV is needed is shown, for example, in this plot on the left, that shows how only using imaging, how you need to constrain the UV part of the spectrum in order to distinguish between a nearby metal poor young galaxy and a farther away dusty galaxy. You really need the UV to discriminate between the two, using only imaging. And of course, UVEX with the spectroscopy, you will also allow to study some of this galaxy over here. So going back to what I was mentioning before with Classy, I was mentioning that the equivalent width of the carbon-3 can be a good tracer, but there is the problem of the turnover, and that very metal poor galaxies are like very low metallicity, can push galaxies into the region of the AGN and shock and to the regions where they are classified as AGN or shocks, but actually they are star forming. Definitely an instrument like UVEX will allow to reveal more objects to test this even more. And also we provide crucial insights for HWO because it will allow to have a great sample of sources to map with the future mission in the UV. But there are limits also for UVEX, because UVEX, yes, will allow to do these kind of studies, but still we are missing something. Everything that I mentioned till now in the UV was integrated spectra. So I was talking about, so COS is a 2.5 arc-second aperture, and also with UVEX we will have a slit, but still we will not have a way to map completely the UV information. And I want to show you this again by showing you 3 classic galaxies. I will go back to this a bit actually in a few slides, but here I just want to show you, I just want to put the focus on J1044 that is shown in green over here. This is the spectrum that we have with COS. We have a Lyman alpha profile that is damped with a tiny bit of emission. We have carbon-4 in emission, carbon-3. And all of this is coming from this region that is shown in yellow here, that is the HST COS aperture. But if we look at the galaxy with the IFU, with the integrated spectroscopy data in the optical, we actually see that there is emission that goes far beyond the COS aperture. with also the 3 regions of star formation that are just next to the COS aperture. So definitely to complete the UV toolkit and to really make our UV toolkit informative to interpret the redshift galaxies, we need spatially resolved diagnostics, even in the UV. And I want to mention how optical integral field spectroscopy revolutionized our way to diagnose the galaxy physical and chemical properties in the nearby universe. I don't have the space in one slide to do this, so I was just thinking in these days, and what I did was I just put very, very few results, so I apologies for the millions of things I couldn't put here. But just to mention, like, I can think about the works from the manga survey, for example, from Belfiore 2016, that showed how the diagnostic for the main ionization source change if you look at the galaxies with the SDSS, so just with one spectrum, or if you use an IFU, because galaxies that would be classified generically as liners, which are shown here in yellow, actually can be very different if you go and look at the spatial distribution of the liner emission. In some cases can be very concentrated in the center, in some cases it's very extended, and these two objects are not the same objects, they're actually two very different galaxies. And many other works studied the spatial distribution of properties, including the gas phase metallicity, for example. And I was thinking about this very nice recent work on a very metal poor galaxy that basically, sorry, I needed a bit of water, that where it was done basically a chemo-dynamic study. Chemo-dynamic studies are the studies where you study both the kinematics and the galaxy properties, and then you go and compare and you try to understand what is going on in the galaxy. And there are clear inhomogeneities in the metallicity distribution of this object and also in the ionization level of the gas distribution that can be interpreted as the presence of accretion and or enrichment. And there are many other works from this point of like similar to this one for other objects. So this is just to say that the information that an integrated spectrum is not the same information that a spatially resolved spectrum can give. So the question is, can we do similar studies in the rest frame UV with HST or not? What do we want or do we need from the future UV spectrograph on HWO? So to answer to these questions, to see like what can we do now with HST, I was also brainstorming a bit with with my collaborators in these days, and I was thinking about spatially resolved studies that have been done in HST with HST using COS, for example. These are some examples. Probably there are many more than these, but this is just to say you take a very nearby galaxy, very metal poor, so can be like it can be an high redshift analog as DDO68 or like a condition similar to the redshift universe like DDO68 or NGC 5253, or even metal rich system like M83, and then you put the COS aperture in different positions and you get the spectrum and you try to resolve in some way the UV properties. So to do this with COS for DDO68, there is a program from Bethan James. The data arrived and there are people working on it at the moment. It took 40 hours of COS to have 7 pointings. And of course, the pointings are not enough to cover like the galaxy, just covering very tiny regions of the system. Same thing has been done for this galaxy, NGC 5253. And here the problem is that you can see that in each COS pointing that has been done, there are actually multiple stellar clusters. So if on the one end, the COS aperture of 2.5 arc-second is not enough to map the galaxy, is also too big because it doesn't allow to disentangle between different stellar clusters. And so different stellar clusters can have different age, can have different feedback in action. different metallicity. So the results that can be done with these are still very limited, and which is why COS can be used to do this kind of studies, but still with limitations. STIS instead has been used, but the STIS spectrograph with respect to COS is not very sensitive in the UV. So I was, so again, brainstorming with collaborators. There have been this work from Crowther in 2016 that is mapping a central ionizing star clusters of 30 Doradus, so the LMC. And it could be possible to map and study the ionizing stellar cluster with STIS, but this is a very bright and nearby object. Another work on 1SVK18 tried to map and study the Lyman alpha distribution. 1SVK18 is one of the most metal-poor star-forming galaxies in our universe. And with more than 10 hours of observations, this was possible. But if you want to do the same kind of study for the other UV lines that I was mentioning before, it would probably take more than 100 hours, if not even more. And if you want to target a galaxy that is not as faint as 1SVK18, so something that is more feasible, let's say, it would still take more than 60 hours using STIS. So there are clear limitations also in this sense. So another approach that has been used with HST was using imaging. That is why I'm going back again to this slide where I'm showing these three classic galaxies, including this J1044 that is shown here from the KSWI map on the right. And so in putting together a cycle 27 program from Matilde and my cycle 29 program and my cycle 29 program, so basically 50 hours. The aim is to use the HST imaging to map the Lyman alpha, the carbon 4, and the carbon 3 for these three galaxies, because these three galaxies show these very different Lyman alpha, carbon 4, and carbon 3 profiles. And we want to understand better how the morphologies of this line can be, and even how the line ratios of this line can be. To do this, it is possible, it is feasible with UV imaging, but it's very complicated. So it is complicated because the UV filters are very broad on HST and are not narrowband filters. You can, for example, are shown here on the left, the filters that we used. So just to show you an example, the Lyman alpha falls here in this position. So it is covered by this filter in blue and this filter in dashed blue. So in theory, to map the Lyman alpha, you can subtract from this filter this other filter. It's not as simple as this because you have to take into account the slope of the spectrum and so on. But this is basically the idea. And you can do the same kind of game, basically, to map the carbon 4 and to map other UV lines. For the carbon 3, instead, it's even more tricky because the carbon 3 is covered by STIS, the STIS filter that has this throughput over here that you can see that is very, very low with respect to the others. So this is why it can be so difficult. But at the moment, this is what can be done with HST. And just to show you very preliminary results on this is what we did for the Lyman alpha. So these are really preliminary, like obtaining these days. So take this with a grain of salt. But this is the Lyman alpha equivalent width. So clearly in the COS aperture, we see that for this galaxy, that is the one in green here, there is a kind of emission, a bit of absorption. So it is reasonable to expect some kind of emission and absorption that are distributed in this kind of way. And then we also see that there is emission beyond the COS aperture. This is the equivalent width, but if you go and see the line flux, you would be able to see a very faint halo of Lyman alpha emission that has been observed in recent studies of Lyman alpha. And for the carbon 4 and carbon 3, it's even more preliminary work in progress, but this is what kind of like the kind of studies that can be done. And this was it has been already very difficult to obtain these very preliminary results, so I can say that it's really complex to use HST imaging to map UV emission lines. And to conclude about this, I think that in these slides, I'm basically collecting, apart from Lyman alpha studies that have been done for more galaxies in the nearby universe, because Lyman alpha is even a brighter line, and also the throughput of the filter is brighter in that specific region of the spectrum. But basically, these are the other UV emission line imaging, mapping that has been done in the nearby universe. So there is one work for the carbon 3, one work for the carbon 4, and one work for the oxygen 6. And this is, I think, that more or less this is it. Like, there are very, very few studies, just to highlight how challenging it is to map UV lines with HST. So I was a bit long, but these are the conclusions that I wanted to highlight in my talk today. So that the surveys like cost surveys like Classy can give crucial insights to interpret the redshift galaxies, because they are giving us a lot of information about the rest frame UV. But we have a limitation due to the fact that we don't have too many metal poor objects, metal poor low stellar mass objects. UVEX represents a nearby future of UV spectroscopy, because with its imaging of sky survey will allow to reveal many more sources to fill that region of the plane that I was showing you before that is unexplored. So very metal poor, very low massive galaxies among all the aims of the UVEX mission, and also to investigate some of them with spectroscopy. So definitely will allow to do also spectroscopy studies. But the UVEX spectrograph is limited in the spectral resolution and also in the spatial resolution. So it will not be possible to do detailed kinematic or spatially resolved studies also with UVEX. And looking at how optical integrative spectroscopy revolutionized our way of diagnosing galaxy properties in terms of physical and chemical properties, it is really imperative that we think about something similar for HWO. So to do integrative spectroscopy UV studies for HWO, because clearly HST is not the right instrument to do this, because the cost aperture is too small or too big, according to what I told you before. So too small to map, but too big to perform detailed spatially resolved studies. This sensitivity is not enough, because is much lower than COS, while the UV filters are too large. So it is feasible to do some kind of UV line mapping, but it's complex and time consuming, and so you cannot have a real sample of objects. So I really liked in one of the talks of this series, I think it was the first one from Jason Tumlison, it was said, and I think that was taken from Michael McDonald's talk from an HWO conference. It was said that the HWO could be like a Muse COS. So an instrument with the field of view of Muse, the spectral resolution of COS, maybe the sensitivity of UVEX. So I wanted to highlight three of the galaxies that I was mentioning during my talk, and thinking about how HWO would see these galaxies. So it would allow to map them in detail. It would allow us to study the stellar and the gas properties with the UV, especially to map the young stellar populations that are providing the stellar feedback on the galaxies, and all the UV diagnostics that I was mentioning before. So with this in mind, so like thinking about how like it would be beautiful to have these galaxies mapped with these UV IFU of the future, I wanted to review with my conclusion. Thank you very much for your attention. I think I was a bit too long, but I hope that this was interesting, and I'm happy to hear your thoughts about it.
That was brilliant and well timed. So fantastic. Thank you so much for the excellent talk. I kept taking notes and started thinking about observation proposals. I guess we're all in that mode a little bit, but yeah, wonderful. So we'll open it up to the floor. Anybody who has either raise a hand or just jump in, let me know. Do I see any hands already? Otherwise, I'm going to have to ask the questions, but I'm leaving that to the last. So, who has a? Oh, somebody had to leave early. Okay. Anybody? I'm learning how to moderate in real time here. Okay, I'll start with one. So not just the low metallicity, low mass universe, but that's sort of also going into the low surface brightness universe. And that can be the outskirts of, for example, a much more massive galaxy, but it could be analog to a low surface brightness environment. We've noticed that a lot of those things are UV red, but optically blue, for example. So their broadband colors are very odd. What was the question? So would it help to go get the UV lines in order to figure out if it's low metallicity or a weird IMF, for example?
This is a very difficult question, and I have to admit I don't have a lot of background on that. Definitely there are so I am not sure if with the current capabilities you would be able to observe that.
Okay.
HST, for example, I'm not sure if this has been done because that is not really my field. The only problem that is what we could see, for example, in Classy, is that you need very specific conditions to see the UV lines. So there are many galaxies that we targeted where we couldn't see any kind of emission line, for example.
Oh.
This is because you need, we found that you need, well, we confirmed because we just have a larger sample, but we found that you really need very low metallicity and also high ionization of the gas to observe the UV lines. This makes it easier. So definitely it's not obvious that if you put, for example, a COS aperture somewhere, you can observe something because the UV lines are very tricky. They are very temperature sensitive.
Okay.
Can be
Yeah. Oh, that makes sense. So then a non-detection would, yeah, not sure what that would tell you then. Yeah, I was looking at sorry, I took a screen grab of your imaging survey. And it's an eye-watering 7% of the light that goes through these
Which
NUV
one?
filters. Oh, it's there's that one. I had a moment of like, wait, is that? Yeah, it's a maximum of 7% of the light goes through. So that's a spot that we could do better in, I think. I had a quick look at the solar blind channel because that's not a very commonly used filter or option on Hubble. And yeah, I think that's all the filters on there, isn't it? I think there's one medium filter left, and that's what it is. And wow, that's a pretty heroic observational effort, I would say. That is the kind of thing like you're pushing the instrument to its limit there.
Yeah. Well, yeah, but we can see something. We can see something.
But
not sure what is the carbon-3 and what is the continuum, but we can see something definitely. And yeah.
Well done. Yeah, I had a moment of like, I wonder if that the ACS has a ramp filter in, but not in the UV. So yeah, it's
these are long pass filters for ACS, and this is actually the cyan filter here is STIS, is a near UV MAMA filter.
Yeah, I think the last thing left was like one medium band, and that's it. So you're using all the filters on a solar blind channel. Oh, wow, that is tricky. Yeah, could you do? So I'm going to open it up, Clayton. Yeah, Clayton, ask your question.
Hi, this is great. UV spectroscopy is going to be a huge player from now on. One of the things that I'm working on right now is like mapping like dust attenuation. And a big issue with dust attenuation, especially in the UV, is the 2175 angstrom bump. I was wondering if there are certain works that are using like this new UV spectroscopy and UVEX, or is there any plans or any ongoing projects that deals with that angstrom bump, the 2175?
So let me check 1 second because I don't remember. It's written here what is the range. So no, it's not written here. Great. Well, UVEX will cover till 2200 something, so it should cover that for the nearby universe. So in galaxies like very metal poor, I think that specific bump should not be there. But definitely, UVEX definitely would allow, for example, to map with high sensitivity also that region of the spectrum. With the costs, I am not pretty sure if, because I mean, for this kind of topics, so for very metal poor galaxies, since you are not like these galaxies are not being found to have that specific bump, and also the range that we probed is between the Lyman alpha and the carbon 3, so within 2000 angstrom. We didn't look into details into that, but definitely like future instruments also like UVEX would cover that as well.
Thank you.
Apologies for not being more informative in my answer.
Oh no, that was great. Thank you.
Any other questions by somebody in the room? Raise your hand or jump in. And I was muted as I asked my question.
Sorry.
So there's narrowband filters on UVEX or not ultrasat, UVEX. And so I noticed that, sorry, UVEX has the Galax filters, ultrasat only has the near UV, Pastor is near UV, Astrosat, the Indian satellite, has a couple of narrowband filters. Have you looked if anyone has done this at all? Because
you know that I'm not sure. I actually don't have. I have not looked too much because I have always worked on spectroscopy, and I recently moved to the imaging side just to do like this UV emission line mapping. So I'm not very expert, but I can definitely check what kind of filters are on ultrasat and other UV emission. For UVEX, I don't remember. I need to check. I would definitely check this because this is because definitely they could allow to do maybe similar studies. Who knows? Definitely UVEX with the slit spectroscopy will allow to map a bit the emission, just doing 2D, like just using the slit, so resolving the emission all over the slit. But still there is a limitation because the slit has there is a limitation of coverage of the. So it's definitely not an IFU that is what many of us would love for HW.
No contest there. This is when we start stacking very narrowband filters, it's out of desperation, kind of. Sorry, Clayton's question sort of reminded me of that because I noticed that they did have a narrow medium band filter that was right on that 2100 angstrom bump. And so instead of having to sort of overlap to wide filters, we could actually just say like, okay, it's this strong, but a bump is not the same thing as an emission line, but that attenuation bump is quite wide. So that's why I sort of went down that rabbit hole. I think it's really interesting to see how we can build up our UV knowledge over the next few years, because we have a bunch of small missions flying, but 150 RF, 150 GRISM spectra is not going to make your life easy at all. So I'm this is very cool to see the Classy do so well. Are there any targets missing from Classy? Would you,
Sorry,
would you expand the parameter space of Classy to
the reason why with the so yeah, I was mentioning before, there is definitely a parameter space that is not completely covered, because in Classy we have one SVK18 that is at very low metallicity around 7, and then we have this gap till 7.40 something. So we have a gap here, mapping the very few percent solar. So one of the reasons why Beth and James started work on this DD068 proposal was also to fill that gap, because DD068 is a very metal poor nearby object with 2-3% solar metallicity, and so we will have more. It's still one single object, but we will have more spectra, and so we will be able to cover a bit that range. It's just that it becomes very difficult. You see, when UV lines are supposed to be bright in the metal poor gas, but still you would need, since it's so faint, an object like this, you need 40 hours of COS to get this data. So that is why it gets tricky, and UVEX will be from this way a game changer, because it will give many more objects in that specific parameter space to follow up with the spectroscopy. But yeah, one of the reasons for the DD068 was definitely to fill the gap for Classy.
Okay. I've been asking somebody ask a question. If not, we're up on the hour. And I would like to thank our speaker, and thank you so much for this absolute masterclass in UV spectroscopy. This was fantastic. Very lovely link to everybody else's. My brain immediately started fizzing, so that's an excellent talk. Thank you so much.
Thank you very much. Bye. Have a good day.
Cheers.